Hi friends, welcome back to my channel Informatics. Today we're going to learn about T Tauri stars. T Tauri stars are stars in the adolescent age. Now for these stars, this stage is a stage of difficulty or a stage of turmoil. So we'll be learning about that in this episode. Now, when we say T Tauri stars, the gravitational contraction still continues. This gravitational contraction begins from when the star was born, like when the star was a protostar. In the last episode, we learned about the protostars, right? So if you haven't watched that video yet, I'll put the link in the description box below, so you can watch it. And then this gravitational contraction still continues, but the T Tauri star is not hot enough to drive thermonuclear reaction. Now we'll be learning about this thermonuclear reaction later. Now a T Tauri star's surface temperature, average T Tauri star's surface temperature is about 4000 degrees Celsius. So that is why it is not yet hot enough. However, it has electrically charged gas inside it. Now inside the gas, atoms are electrically neutral because the amount of positive charge, the quantities of positive charge and negative charge is equal. All right, they are equal. However, when the gas is hot enough, when it is heated, the atoms shake apart, and this process is known as ionization, and the atomic fragments are known as ions. So this T Tauri star is filled with electrically charged gas known as plasma. Now a T Tauri star, when we compare this star with our sun, we can say that an average T Tauri star is more bigger, it is larger than the sun, and it rotates more faster. Because our sun takes 1 month to rotate on its own axis, the T Tauri star takes a few days. So it rotates really faster than our rotates. When the star rotates, it produces a magnetic field, like a wire with an electric current. It generates a magnetic field around it, right? The same way, the T Tauri star or many other stars, normal stars, they produces magnetic field. However, when we come to in the case of T Tauri stars, we can say that their magnetic field is more powerful because T Tauri stars rotate faster than normal stars. Like as I told you before, T Tauri star rotates faster than our sun. Now, around this T Tauri star, there's a protoplanetary disk. This disk was formed when the star was born, when it was protostar. If you remember, this is known as the giant molecular cloud. It turned to a globule, and this is the same disk, the protoplanetary disk. When this magnetic field reacts, when they interact with this disk, streams of gas flow out. They are sucked out of the disk and they touch the surface of this T Tauri star. Now when they touch these gas streams, when they touch the surface, the T Tauri star reacts with powerful magnetic flares. And this is a hallmark, or this is an example of a T Tauri star's formation, like the star, the growing up stage. Okay, so this is an example. And a final characteristic of the T Tauri star is that the ions are blustered away. They bluster away into deep space. That is like, it is a stellar wind, all right? And if we compare the stellar wind with the wind in our solar system, the wind produced by our sun, the solar winds, this stellar wind is more stronger, all right, than the one in, the sun also had a T Tauri stage, right? In its T Tauri stage, it had a more powerful wind than the wind it is producing now. Now, the period of this T Tauri stage depends on the star's mass. For example, our sun's T Tauri stage was 30 million years. All right, 30 million years. And then in all common events, there is a common event that stops this T Tauri stage. When the T Tauri stage ends, the gravitational contraction ends too. And then this stage, the next stage, the astronomers call this stage a main sequence. Our sun is in the main sequence stage right now. It's a main sequence star. So when a star is in its main sequence period is the longest period in a star's lifetime because it drives thermonuclear reaction. Thermonuclear reaction is when the internal thermometer inside the interior of the star, when the thermometer clocks up to 10 to 15 million degrees Celsius. In this extreme heat, positive hydrogen ions, they move so quickly that when they hit each other, they overcome their mutual electrostatic repulsion. Now this means like when we put positive and positive together, they rebound from each other, right? They repulse from each other. So the same way, it's not like the same way, because in this extreme heat, they overcome this repulsion and then they stick together. And then slowly the star, the main sequence star, our sun, are sun-like stars, all right? So they consume this hydrogen, positive hydrogen, and then they convert into a new element known as helium. They convert hydrogen into helium. And this is known as stellar nucleosynthesis. This helps to produce new large amounts of energy and an outward pressure. Now, this is the first time in the star's lifetime it is producing an outward pressure. Till now, it has been grasping the gravity around it. So until now, it has been doing this, but from now, it will produce outward pressure. Now, the astronomers call this situation hydrostatic equilibrium. All right, the star producing, it releases a huge amount of energy and it releases an outward pressure into space. This situation is known as hydrostatic equilibrium. As I told you before, the T Tauri stage depends on the star's mass. So if it's a very large star, it has to depend on its coarse weight, right? It has to convert more hydrogen into helium to produce its outward pressure. So it will tear through this stockpile of hydrogen in a few million years. It will take a short time. However, if it's a smaller star, like smaller than our sun, it will take more time to convert hydrogen into helium. An example of this smaller stars is like red dwarfs, and that's what we're going to learn about in the next episode. Hope you guys enjoyed learning about these T Tauri stars and main sequence stars in this episode. Alright, so I'll see you guys in the next video. Thanks for watching. Bye bye.